Welcome, this is Dennis Helsel, and this topic today is the mystery of Nondetects, how censored data methods work. And as I stated in the write-up that you saw when you registered, one of the most frequent questions I'm asked is what numbers do I put in for Nondetects in order to do various procedures using data that have Nondetects? And the answer is, for the good methods, you don't have to, and you shouldn't. And so today I'm going to try to explain why that is true. So the objectives here are first to demonstrate how censored data methods work without putting in a value for Nondetects, because you don't know a value for Nondetects. So putting in one is immediately incorrect and can lead to a number of problems. Second, I want to motivate you to use these methods called censored data methods, go also by the name survival analysis methods, by increasing your understanding of them and then also your trust in them because of understanding them better. And I admit that things have not been explained well in the past. So it's often that you have to jump over into another discipline in order to see good examples of those being used, although that has improved over the last few years in environmental science. And third, I want to highlight one of the aspects, since this is part of the new online course, Nondetects and Data Analysis, that's available on our training page. And so you could sign up to take that class, which goes into detail on all of the methods having to do with Nondetects. And you could go and look at the outline there and see what's contained in it. If you have questions about that further than what's online, just go ahead and shoot me an email. All right, so we're going to talk about three methods for estimating statistics like means and standard deviations or medians or 90th percentiles or whatever. And those three methods are maximum likelihood, Kaplan-Meier, and ROS. And to illustrate those, I'm going to use three different types of plots: PDFs, CDFs, and QQ plots that I hope will make understanding how those methods work a bit more clear. And towards the end, we will also look at some things about hypothesis tests using Nondetects, whether there's one detection limit or multiple detection limits. The main idea in all of these methods is you do not stick in a number, 1/2 the detection limit, 3/4, or whatever your favorite proportion is, 1/2 or 3/4 of the detection limit. You don't put those numbers in. You don't need to put those numbers in with these methods. So I'm going to start with a poll here. So this is a slide that helps me to remember. All right, so the poll is, have you already used any of these methods, such as Kaplan-Meier, ROS, etc.? And you can choose either yes or no. I won't see the answers categorized by who you are, so feel free to choose the answer that's true. And I'll wait just a moment, but not very long. I'm just curious to see how many people have used these and how many people have not. I think there will be something in this webinar for both groups. All right, since that isn't real complicated and I don't see the numbers changing much, we'll go ahead and go on and take a look. And it's about 60-40, something like that. So that's good. That's good. There's both people that are here that have not used them. And so hopefully after today, you'll have a better understanding of why you should. And people who have used them, and hopefully by the end of the day, you'll have a better understanding of what you've done. So let's go ahead and get to it. All right, first, I'm going to be illustrating maximum likelihood using this thing called the probability density function. Think of it first off as just a histogram of the data. So that's what the gray bars are here. And then what maximum likelihood methods do is fit a particular shape to that histogram. You tell it what shape you want to use in terms of a class, and those things are like a normal distribution, so that's what this is, a nice bell-shaped curve, or a log normal distribution, or some other type of distribution, and that distribution has a mathematical function, and that function has a shape. And so here is the normal distribution, the bell-shaped curve. On this plot, because the y-axis is frequency, it's the counts of the number of values in these bins, in these categories that are represented by the bars. The total area under this curve is going to be the sample size n. Usually, and the rest of the graphs that you'll see, this is scaled, that this instead of frequency is divided by n, and so you get a proportion in each of these bars, and then the area under the curve is 1. So a PDF is just a plot of how often different categories of values occur in the data set, and this curve is a model of that, a nice smooth curve that at any point for any value on a continuous scale, the scale is on the x-axis for things like concentrations, at that point you can get back a probability or a frequency of how often that would occur. So here's a picture of 3 different normal distributions, and they have different standard deviations. And the one with the solid line is the one that has the smallest standard deviation. And that as the standard deviation increases, things spread out. So one of the ways that maximum likelihood works is to vary the standard deviation to fit what your data, fit what that histogram looks like. I do have a note here that particularly for the normal distribution, if you get much in the way of a standard deviation, a larger standard deviation, you'll often see the curve go down past 0. So all the values to the left of 0 here, all the proportions are saying that there is, let's see, if I go from 0 up to the dashed green line for the middle normal distribution and come over, it looks like there's about 5% of the data at that one point at 0, and then the area totaling that up to this, to the left side, might be something like 10% perhaps, maybe a little more. So there's some percentage of the data that are being modeled as, and so expected to be negative. So that's a real downside for using a normal distribution. Here's another type of distribution, a log normal, well, actually 2 types of distributions, a log normal distribution and a gamma distribution. They're both skewed distributions, which means they're not symmetric. The left half, if you split it down the middle somewhere, the left half does not look exactly the same as the right half. They also don't go below 0, which is one of the real strengths for using them as a model. So in maximum likelihood, you will have to tell it which of these distributions you want to use. You can do that by comparing them with different kinds of plots. QQ plots or probability plots, which we'll talk about later, are one of the best plots to use. And if you've been at any of the previous monthly webinars, you've seen that sort of thing being done. There are tests like the Shapiro-Wilk test and others to see which distribution fit well. So using those tools, you can decide which to use. You can see here that the log normal, this is a log normal and gamma distribution, each fit so that they have the same mean. They were fit to the same data set. And so you can see that for the log normal, what that does is it pushes the bulk of the data down a little bit lower than the gamma distribution does. But then at the other side, the probability of seeing some high outliers offsets that. So there's a higher probability of seeing some outliers with the log normal than with the gamma. So there's nothing right or wrong about either of these other than which one fits the data that you're working with the best. So you tell it which one of these to use, and then MLE will optimize that. Here's 3 different log normal distributions. And so if you tell it that you want to use a log normal, it's going to find the best standard deviation, which is the main thing that's changing this shape. It's called scale up here because it's the standard deviation in log units. So here with the solid curve is one that has a fairly small standard deviation, and it looks pretty much like a normal distribution. The log normal distribution is a very flexible distribution in terms of shape, and it only has just a little bit more area to the right than it does to the left down towards the bottom. And so there's a little bit higher probability of getting a higher value, somewhere around 1.8, than there is the lower value on the other side. That's the only indication here that this is not a normal distribution. So if you had a data set of modest size, like 20 or 30 observations, you might, and it came truly from this distribution, you might not be able to tell that it's not a normal distribution visually. So a log normal can be as close as very close to a normal distribution, or with an increased standard deviation, it's going to look more skewed like these others. So maximum likelihood varies the standard deviation until it finds the best fit to your data. Here are two other log normal distributions. We could also kind of give you a picture of changing the mean. And so I'm going to do that here because that's the other thing that maximum likelihood does, is it changes the mean as well as the standard deviation by slight amounts until it comes to decide what to do, how to fit the data to the data, how to fit the distribution to the data that you have. So it would change the mean doing something like this, and that's just going to shift it back and forth. And the goal here is for this curve to fit kind of about halfway through the tops of the bars. Something like that would be a good fit. And so by changing the mean back and forth, changing the standard deviation numerically, not graphically, but by doing that, maximum likelihood finds the best means and standard deviations. Now with censored data, we have the left side of this set of histograms gone because they're below a detection limit. So we don't know how to put the bars in here. What we do know is the proportion of data that are less than, in this case, just one detection limit, although everything I'm going to say applies for multiple detection limits as well. But just to illustrate this, what we know is that there's 14% of the data below 2 in this data set. They're less than 2. So we've got 14% of the observations to the left of this vertical blue line. And when we fit the distribution, we're going to fit, by MLE, we're going to fit this with two pieces of information. One, how well can I fit the detected values? So going through the bars on the histogram, how well can I match that? And two, how well can I match the proportion of the data set that ends up to the left of 2? So in this case, with the best fit, maximum likelihood decides that there's 12% of the data underneath this curve that is the best fit curve to this data set. So we've come close with having 12% being close to 14%, and apparently by trying to make it 14%, that decreases the fit here for the detected values. And so it's a trade-off. And there's a mathematical rule on how you can find the best fit. It's something called the log likelihood. I won't go into that today. We go into that in the class that's online, and show how that optimization procedure, which is what it is, works. But you can understand the trade-off there. And so this curve with this mean and standard deviation, whatever that is, becomes the best fit maximum likelihood result. And so the idea with maximum likelihood is that this is the distribution, once you've picked that it's a log normal, this is the distribution that has the maximum likelihood of producing the data that you've observed. You can do this in software. Here's two routines in the R software, the NADA package and the ENV stats package. And so you tell it you want a log normal by this command, where the L norm says, I want this to be a log normal. And it gives you back information. It tells you that there's only one censoring level, one detection limit at 5 for this data set. This data set came from a US EPA publication, the Unified Guidance, back in 2009. And it has 62.5% of its data below the one detection limit of 5. In doing this fitting the curve to the other 30-some% here of the data represented by these histograms, and leaving a space that should be pretty close to 62.5% of the area under the curve, below 5. It fits a mean of 4.84, a CV here, a standard deviation up here. You can translate one to the other pretty easily. So depending on the package, what it gives you. There were 24 observations and so on. It can even give you a confidence interval around that mean, or a one-sided UCL around that mean, once we fit the distribution to this. So it's very useful. This log normal type of approach is very helpful, because it's what you cannot do is take logs and fit a nice normal to the logarithms, transform that back, and get a confidence interval in the original units, because when it's a confidence interval on the mean of the logs, and when you transform it back, it's no longer a mean in the original units, it's a geometric mean. And the confidence interval you get back doing that kind of process is a confidence interval on the geometric mean. And that's not really what you want usually when you have a UCL. You're interested in an upper confidence limit on the mean itself. And so this kind of procedure allows you to do that. All three of the procedures we're going to talk about today allow you to do that. So MLE, maximum likelihood, you must assume a distribution and you decide which one to use. No substituted values are used. The non-detects are represented by the proportion of data that are below each detection limit. And it's a fitting and optimization procedure. It's a pretty sensitive procedure, and so it needs data. You need to feed it data. So in general, a rule of thumb, there's nothing that I can tell you other than from experience, around 50 or more observations, both detects and non-detects totaling 50. I would recommend prior to using maximum likelihood, at least in most cases. The more skewed the data are, the more difficult it is to fit. So if you had something that looked like a normal, you could get away with something smaller, but generally around 50 or more. So oftentimes we don't have 50 observations. What do we do in that case? Here's a second method. I'm going to end up talking about Kaplan-Meier. So first, what are the graphs here? Well, this is just the PDFs. Actually, it's the smooth curve version of them, of a normal distribution. And you can go in and say, I want the 10th percentile for this curve. So if I have 10% of my data below a value of 1.71, that's the area that's shown in the color right here. So I could take that and go over to a different kind of plot, one that accumulates these areas, called a cumulative distribution function. So it's basically plotting percentiles. And we're going to fit a curve, an S-shaped curve for a normal distribution that has a value of 1.71, and that hits right at, on the vertical axis, the 10th percentile. 10% of the data are at 1.71 or below. Can do the same for the 50th percentile, the median. For a normal, that's also the mean. Value of 2.94, and that's at the 50th percentile. Do the same for the 80th percentile. 80% of the area under the curve is in this color up at the top. And so at the 80th percentile, you're up here on the cumulative distribution function. So this S-shaped curve representing a normal distribution is the cumulative distribution function. And the nice smooth curve is the theoretical normal that's fit here to the data. And these step functions, these little steps that go up, this is a fairly large data set. Each step is a step at a different value. Could be one value that jumps up, or it could be three values if they're tied, and they'll jump up a little bit higher. And so the data are represented by a step function, and we want to fit something to that. All right, how does that relate to anything else? Well, the Kaplan-Meier method is a non-parametric method, and it works in this way, and it's very easy to demonstrate with a CDF. So I have a small data set of numbers that I just made up. There's 10 values to make it simple. So there's going to be 10 jumps up with this step function, because there'll be 9 jumps up. I do have 2 tied values at 0.91. So there's a double jump here. So there's 9 jumps up. And the first value is 0.38. So this EDF or CDF, sometimes called the empirical distribution function when it's dealing with sample data that you've collected, jumps up at the first value of 0.38. How far does it jump up? It's the weight that that observation has when you're thinking about computing a mean, the weight of the observation. And so each of these observations have an equal weight. There's 10 of them, so its height is going to be 1/10. So this jumps up to holding 10% of the area. If you think of this rectangle here that has a color as the area representing that value of 0.38. And then we go to the next one, the 0.77 does the same thing, goes out to 0.77 and jumps up. How far does it jump up? 0.1, 1/10. Same thing for the third and so on. So we can do this all the way till the top. And this area here that's colored in represents the full data set. It actually is a histogram, if you want to think of that, or a bar chart would be better. A bar chart lying on its side where these bars go up to each value in the data set, and each bar has the same width, which is the weight. Well, if you think about what a mean is, you sum the data up and divide by the sample size n. So that's the same thing as summing up 0.1, which is each individual data value's weight, by the data value itself, and that happens to be the area of each of these bars. So these bars that are colored in from the value going down to 0, that area is a representation of the mean. So you could sum these up and divide by n and see that the mean is 1.35. So this is the relationship between a mean and the cumulative distribution function for that set of data. So what Kaplan-Meier does is say, well, when I have a non-detect, I don't have a value to plot that at. So I really don't have a bar that I can assign to it. So I'm going to reassign its probability, that 0.1, the 1/10 in this case, down to the detected data that are below it. So it's saying I'm going to use a non-parametric model. I'm not going to assume a model of a normal distribution or a log normal distribution or anything else. My model for what's below a detection limit, say below 5, is the observed shape of the data that I can tell below that 5. So if there are detected values below that 5, then I'm going to assign to each of those detected values a bit of the probability that this less than 5 represented. And once I get down to the lowest detection limit, I'm here assuming that you have the lowest detection limit. Everything below that limit is a less than. So maybe that's down at less than 1. Then those at the lowest detection limit for Kaplan-Meier are treated as detected values. So they're going to have a value. Usually it's assigned the detection limit itself. That below that, so if there is one value that's less than 1, it's going to have a weight just like it was a detected 1. So what this means is that if there is only one detection limit, Kaplan-Meier in essence substitutes the detection limit for that non-detect, or the number of non-detects at that detection limit. So it's less useful than other methods when there's only one detection limit. And then really the criteria, I think I say this somewhere else in the slides, the criteria is what's the proportion of data below that lowest detection limit. If that proportion of data is small, then calling those a detect at that detection limit is probably not all that important. And that's often the case when you have multiple detection limits, even though I think there's a better method than this in that case. But for the data set that we just had a minute ago, this copper data, I purposely picked one that had 62.5%. So what the CDF is telling you of the detected values plotted with the step functions and this huge step at the detection limit, that this area in Kaplan-Meier is going to be huge. It's going to be much larger than it should be. We know those values are less than 5, and yet they're 62.5% of the data outlined by the almost the square, the rectangle that I'm outlining here with the cursor. That's much larger than it should be. These should be going down with steps, but we don't know what those steps are. So Kaplan-Meier is going to overestimate the mean in that situation. Okay, back a slide. And so here's what Kaplan-Meier does. Starting at the top, these first 4 values, or 5 values actually, are detected values over here. They haven't changed from before. They have the same bar width, the value for the concentration, if that's what this is, and they have the same weight, the 1/10. Now we hit a 0.91 that I have said the lab told me was less than 1. I don't have a bar for that here. There's one fewer bar here than there was before. So what do I do? This value that was 0.1 representing the weight, the information that's in this less than 1 now is going to be redistributed down to the detected values and the lowest non-detect further down. And that will happen for each of the detection limits. So this bar, which represents the detected 0.91, has a height of 0.125 now, not 0.10. The 0.81 has a height of 0.125. The 0.77 has a height of 0.125, and the 0.5, which is the lowest non-detected value, is treated as a detect, and it has a weight of 0.125. From that, you can, just as we did before, sum these areas up, and that will be the Kaplan-Meier mean. In this case, it's 1.33. Pretty close to what it was before. I've left the older CDF, the one before I censored those 2 numbers here in, I think it's blue, just to see the difference between them. That's how Kaplan-Meier works. It says that my best estimate of what's happening below 1 is just what I've observed below 1. And so bumps up the weight for each of those observations a bit. So you can do Kaplan-Meier in the packages, in any package that has survival analysis, and that's every commercial package. And here is in R, this NPAR, the piece that says NPAR, that means non-parametric, and it will give you back Kaplan-Meier estimates of the mean and standard deviation for this data. Tell you that it's 62.5%. If I had asked it to, it would have computed an upper confidence limit. It doesn't really have a value for the median because that median is below 5. 62.5% of the data are below 5. So it can only tell you that the median is less than 5. That's not a bad estimate, but it's one where you're not assuming anything about this shape of the data. So Kaplan-Meier does not assume a distribution. That's good generally. No substitution is used. That's good, very good. Non-detects affect the computations of the mean and standard deviation of percentiles through the observed percentage of values below each detection limit and how it redistributes that probability down to the other detected values underneath it. It works best with more than one detection limit. Technically, it works best, it works well when the proportion of data below the lowest detection limit is small. That's really the critical issue. All right, if that's not satisfactory because the detection limit value is used for the lowest non-detect values, here's an alternative. This is something called ROS, and it's based on a QQ or probability plot. We've seen these before in the past lectures. You're probably familiar with comparing things to something like a normal distribution with these. What is plotted with censored data with non-detects are the detected values, because of those are the values that we have concentrations for. Here we've got on the y-axis the logs of those copper concentrations. We have space here that's allocated for the percent of non-detects. And so since there was one detection limit, it's a big gap here, 62.5% in terms of a percentage going less than left to right is allocated to a space here. And we do not plot numbers because we don't know what those numbers are. What that does is push these detected values to the same percentage points that they would have if we knew what these values are, which means I can trust this shape. And as I mentioned in past webinars, if you delete the non-detects, that is not true. These detected values get plotted at the wrong percentiles. If you stick in a half or something like that, it will also push these detected values to the right percentiles, but the information, if you want to call it that you have here is totally wrong, because you have numbers that are all at one number. It's like a flat line here, and it totally distorts an evaluation of what kind of distribution do I have. So here we can just use the detected values plus the spacing, and I'm just re-emphasizing that that's the two pieces of information with censored data: the values for the detected data and the spacing, the proportion of data below each detection limit that is used with these methods. So we can fit a line to this, and that represents a distribution. So this is a mixture kind of procedure. For the detected values, there's no assumption of a distribution. But for the non-detects, we're going to use what we see of the detected values to project down, so that I don't have to just say everything less than 5 is 5, like Kaplan-Meier does. I want to have some sort of model for how to extrapolate down below the lowest detection limit. And that's what ROS does. So here the logs are on the y-axis. And this is going to be, I'll show you in the next slide why. This is a representation of a normal distribution. This is a normal probability plot using the logs. So this is representing a log normal assumption of a log normal shape for this data. These are percentiles. You can see they're in a very nonlinear scale. These are percentiles for a normal distribution. They're smashed together a little more closely in the center and spread out as you go to each end. That's because it's representing the bell shape of a bell-shaped curve. Usually in these plots, that scale is transformed into a linear scale. And this linear scale are something called normal quantiles. And so what that is a center of 0 that represents the mean and the median. And then it goes up in units of standard deviation and down in units of standard deviation. This is 1 standard deviation above the mean. Gives you the same look to the plot. Still leaves the space for 62.5% of the data. So this is how you would usually see it coming out of software. So what does ROS do? What ROS does is take the numbers, we know the numbers of non-detects, not their values. And from the numbers, we can say, I want to evenly space numbers in probability space. So we're spacing it evenly from 0 to 62.5% of the data. We're spacing it evenly, not in concentration space, but in the space of probability. So we're representing even distances on that CDF, if you want to think of it that way. That is even in those percentiles that were on the previous graph. So it looks here like things are put together a little bit more closely towards the center, and as you get out towards the end, they're spaced out. What that does is that means that these points are representing a normal distribution by doing that. And so that's why they're unequally spaced on this plot. So what we're doing is putting in, I would call them placeholders, or I would call them air pillows. We're trying to hold these detected values in their proper positions. And we're doing that in a way that they are spaced here to represent a normal distribution. And these are going to then be said, okay, I have a point right here. When I come over, it's 1.51. That's a number. I'm going to use that number. This is something called imputation in statistics. Imputation means I'm creating a number from a model, and that's really important. I'm creating a number from a model. Substitution, putting in a half the detection limit, is not imputation. It's substitution. I often call it fabrication. There is no intelligence used in saying 1/2 the detection limit or 2/3 or any of the numbers. It's arbitrary which number you would pick. There's no way to know one being better than the other with substitution. Here we have a model that these data are going to come down here as a normal distribution. So it's really just an alternative way of doing what MLE does, fitting a distribution to a data. And it's fitting it in the way that we're going to hold the correct percentage of data below the detection limit. Say a little bit more about that. So when we take E, because these were natural logs E to 1.51, we get this number. These numbers collectively, and that's important, collectively are used with these detected values in the way you would normally do. Sum them up, divide by n, and you get an estimate of the mean. That's the ROS estimate of the mean. Compute a standard deviation from them. That's an estimate of the standard deviation. That would be a reasonable estimate if the data that you don't have values for, that are the non-detects, did look like a log normal distribution. So these numbers have in them the information that this was generated from a log normal. These are imputed numbers. The result is a non-parametric method in regard to the detects, the values that we know, and a parametric method, assuming a distribution, in regards to the non-detects. That makes it less sensitive to an assumption of a distribution like the log normal than is MLE. That makes it easier to use with smaller data sets. You can't get into as much trouble here, especially for estimating the mean and things like a confidence interval on the mean, because the mean is more strongly affected by the higher numbers, which we know, than the lower numbers that we don't know. So ROS has some of the properties of a distributional method, including I can extrapolate below this detection limit. And that gives me an estimate without just calling it the detection limit itself. That's a good thing. But some of the properties of a non-parametric method, it's not assuming that you're right on that straight line for the detected data. So that's a good thing. And so this is, for my opinion, the most usable of these three methods across different sample sizes, different assurances of how well you know the distribution. You can do it in the NADA package. I think this, let's see, I didn't give you one. You can do this in the NADA package. You can do it in the ENV stats package and so on. You can get an estimate of the mean. You can get an estimate of a confidence limit, an upper confidence limit, and so on. It's using the information in the detects and the non-detects by their proportions. Those proportions are spaced out based on a distribution, and it works fine with multiple detection limits. So ROS, a distribution must be assumed, but only for modeling the non-detect portion. There's no substitution. I'm using that word purposely instead of imputation. There's no irrational putting in of numbers. There's a model-based putting in of numbers. And they're only used collectively. Let me go back to that and make one more point. These numbers they are not estimates of what was in a particular sample, a particular bottle of water or bag of dirt. There's no way to assign these to those, no ways that make sense. You've got here maybe 12 or so less than fives, and you had 12 results in different locations and different times that were less than fives. There's no way to assign this number 4.206 to any one of those. And so you shouldn't do that. Don't do that. These are collectively used to represent the distribution. So do not take these numbers and plug them in and use them in a t-test. Do not take these numbers, plug them in, and run principal components. I've seen both of those done. There's no way to assign this number to a particular sample, particular observation. When it is done and you do that yourself, you're probably assigning them just in this order because they get generated in this order, and the order of the observations is the order that they are in your data set, whatever that is, ordered by time, by alphabetical order, or whatever. It's really a totally arbitrary assignment, so don't do that. Okay, I think I beat that enough. So if you compare these methods on this table here, basically blue is good, red's not so good, and the method that has the least red is the ROS. You can see for this copper data, the three means that were computed. You can see that the Kaplan-Meier method is a lot higher. It's biased high because it assigns the detection limit value to all the lowest detection limit data. And that it would be better choice to use one of the other two. And I think we said there were 24 observations. That means that this assumption of a log normal might not be the best assumption. Why? Because I've only got 24 observations to fit it. The really difficult thing to fit with MLE is the standard deviation. It's very sensitive. The shape of that curve, as we saw in some of the graphs, are very sensitive to the standard deviation. So maybe this isn't quite correct. This is less sensitive to that assumption. So that would be my choice in this case. So that's estimating statistics and things like UCLs and confidence intervals. Let's move to testing group differences. Won't spend a long time on this. There's a lot of information on this in other places, in newsletters, on our site, in a textbook that I wrote years ago. Just like the mean is a standardized total, it's the number of observations divided by n. The probability is a standardized rank. Rank is often abbreviated I. It's the values 1 through n, 1 through 24. If you have 24 observations, the lowest value gets a rank of 1. Dividing that by n plus 1, I don't know why that parenthesis is there. It's in the wrong spot, should be parenthesis n plus 1, sorry. The rank over n plus 1 is the probability to declare something as a percentile. So the median would be at the 50th percentile at a value of 0.5. It would be halfway through the data set. It would be 1/2 of the distance between 1 and n plus 1. So ranks are a measure of the relative order in the data set. They are strongly related to percentiles. So the tests on ranks are basically tests on differences in percentiles. So they're tests on, do I see most of the low data, the data with the low percentiles in one group and the data with high percentiles in the other group? Here's a set of data, one of the data sets that comes with the NADA package. This is lead in blood of herons that were exposed to high levels of lead environmentally and low levels of lead over here. And they wanted to know whether that shows up in the blood. There is one detection limit, again, to keep things simple, but these tests work for multiple detection limits just fine. This detection limit is at 0.02. The percent less than 0.02, that's the information. That percentage in the high group here is less in this group than it is over to the right, the percentage of that data set in the low group. In other words, I can see the median here in the high group. In the box plot, it's above the detection limit. I've got less than 50% of the data below 0.02 in the high group. Over here, I cannot see the median. I know it's estimated in there, but it's down below the red line. Everything below the red line is an ROS estimate. So you cannot see in the raw data what the median is. It would just be less than 0.02. So I've got more than 50%, at least 50%, if it were right on the median, probably in this case, more than 50% of the data below 0.02. That information is used in these tests as well as the detected observations to say which group tends to be higher than the other. There's a lot more low data in this low group than there is in the high group. So it's using that information of the percent of values below a detection limit or multiple detection limits to make the judgment of which group is higher than the other and whether there is a difference. The Wilcoxon rank sum test should be a familiar test to many of you. If you have only one detection limit, you can use standard non-parametric tests to do this kind of thing, nothing unusual. Because they will rank the data appropriately, they will rank all of these detected values individually with the high ranks. They will rank all the non-detects in both groups as identical to each other. They will be tied. And it's the proportion of those low ranks that will distinguish the groups based on the non-detect values. You can do a little bit fancier methods than just the Wilcoxon rank sum test, but they're very similar in concept, using something called scores. Scores are just modified ranks. They are essentially equal to percentiles computed by, or strongly related, let's put it that way, to the percentiles computed by the Kaplan-Meier method that we've already seen. So what they do allow is for you to have different ranks for values that are less than 1 versus less than 5s. And those ranks are the ranks of the detected values, including the detected values in between 1 and 5. So it's going to use the information in the proportion of data below 1 and the information in the portion of data below 5 to rank data like values between 1 and 5 that are detected. In those percentiles, thinking of them that way, those percentiles are adjusted for all the proportions of data below 1, below 5, and below any other detection limit that is there. So it gives you back numbers that can be used in something very much like, they're really just generalizations of the rank sum test or the Kruskal-Wallis test, either one. They're numbers that are used. There's going to be one of those numbers for every detected value in the data set, and they're basically evaluating whether the percentiles are the same in the two groups. You've got both low and high percentiles in both groups. You've got both similar amounts, proportion of low data in both groups, or whether one group tends to be higher and have higher percentiles than the other. The high percentiles are all aggregated in one or a few groups. So that kind of test is one of the names is the Pareto test, and that's what's run in R. There's variations of these that really just change that test statistic slightly, the evaluation of what kind of percentile I'm assigning to these. And so those other names go by Pareto-Prentice, Generalized Wilcoxon, the Gehan test, and other names. They're very similar. You'll find at least one of these, if not more of them, in any package that does survival analysis. You can find them in the NADA package and in the ENV stats package in R. If you want to know more about them than what we have time for today, you can go to the newsletters that are on our site and read about them, or you can take the class that is up on the web now. So we can do things like comparing multiple groups. This would be a censored data version of the Kruskal-Wallis test, and you saw this if you were in one of the webinars in the last few months. So this is 4 groups of data, one detection limit at 0.05, but varying amounts of data, proportions of data in each of these groups below 0.05. The groups labeled 3 and 4 here have almost all or high proportion of values below 0.05, and the groups labeled 1 and 2 are much higher. And you can see that in these box plots, and you could see it in a test that would test that these two groups are different than the 2 groups, the 3 and 4 groups. You can plot CDFs with these step functions and see the same thing. These were the high groups. These were the low groups. Here, you start to hit detects at about the 10th percentile in the high groups. You don't hit detects until you get up around the 70th or higher percentile in the low groups. So there's 70 to 80% of the data below 0.05 here for the low groups. There's only 10% of the data or less in the 2 high groups. Okay, and these test out as being significantly different between the 2 high groups and the 2 low groups. Here's a way of doing that test. Again, this repeats something in the past webinars. So you can get back p-values. You can get back p-values for the individual comparisons among the groups, as well as an overall test like the Kruskal-Wallis. This would just be a Kruskal-Wallis with data that has 1 or more detection limits. And it's a very small p-value showing that those 2 high groups are very different than those 2 low groups. You can see where I go into a bit more detail in that in this webinar. If you weren't attending it in person, you can find that up on our training site, which is practicalstats.teachable.com. So in summary, censored data methods use the information in the detected values plus in the percent of data below each detection limit to compute statistics and do hypothesis tests. You don't put in values for the non-detects because you don't need them. What you need is how many and what proportion are those non-detects. The ROS imputed values, again, to hit the same point over again, are air pillows. They're not estimates of what was in the samples. They're there to hold the space according to that particular distribution. They're not used individually or should not be used individually, only collectively. Don't use them plugging them into other tests or procedures. With one detection limit, you can do familiar non-parametric tests like the rank sum and Kruskal-Wallis test. If there's more than one detection limit, those other tests are available. They're just extensions of these tests to when you have multiple detection limits, but they're in the survival analysis package. They have these names that sound strange, pedo, what's that? They've been used for decades in other disciplines. So you could find those in the software that you are able to use. Thank you for attending. Let me look at the questions now. First one from Russell. While I'm thinking about it, I've seen some people reporting a negative value for the LCL. I think that is nonsense since concentrations can't be negative, only less than some number. That is true. And so when you see that, you know that they didn't use the right method. If they were trying to do something with censored data, then they must have used a normal distribution rather than one of those skewed distributions that stop at 0. And you certainly don't want to do t-intervals, plus and minus, and get negative numbers, whether data are censored or not. If you get a negative number for the LCL, it tells you that you've done the wrong thing. Okay. We have contaminant concentration data. I'm using the NADA package. So far, I use the value of the method detection limit to calculate the mean. And then I specify that this is censored. That's generally how the NADA package and other packages are put in. The information that something is less than 5, let's say, when you put that in to a set of data, has to be, you need the indicator that it's less than, and you need the 5. You need to know what it is that it is less than. And so you need 2 columns for these kinds of censored data. And that's the way that all these packages use. There's 2 formats. If you want to know more about the other format, you can take the class or look in that book that I wrote in 2012. But the atypical format, one of the 2, is to have the detection limit number in one column, and it's in the column with the detected values. And then you have an indicator column, and that indicator column, often 1 zeros or true falses, but it could be other things. It could be a less than versus a blank. Some indicator in that other column tells you which numbers are detected values and which numbers are less thans. So it sounds like you're doing it properly from what I can tell. For robust ROS, do you generally select the log normal distribution or select the distribution of detected results? If you can do a better fit than log normal to a QQ plot, we talked about how to do that a few months ago, then I would pick the other distribution. If something else fits, if a gamma distribution, the other skewed distribution that's common, fits better, use that. There's nothing magic about a log normal. In the type of data that I work with, if it has a lot of non-detects, then it has a lot of stuff smashed down close to 0, which tells you right there a normal distribution is not going to work very well. So I rarely pick a normal because a normal distribution rarely fits data well that have non-detects, and it almost always starts to shoot the end of that distribution down below 0 and you get negatives, which is really an indication that you don't want to use that. So log normal and gamma, and just use the one that fits the best would be fine. I would say about 80% of the time of the data sets that I use, log normal fits best, but that doesn't necessarily hold for your particular data set. All right, let me skip down a little more. So would you recommend not assigning the ROS imputed values for use in trend tests? Yes, definitely. I would not recommend doing that. If not, how do you run a trend test with data with detection limits or multiple detection limits? There are methods that do that, again, use the percentages. You can do regression. You can do a Thiel-Sen, seasonal Kendall kind of procedure with non-detects. Maybe I'll make one of the next webinars on that topic. We'll see. It's in the book that I wrote in 2012. It's called Statistics for Censored Environmental Data, and then a little bit more phrase on what software was used. Or you can take the class that's up online now, and we cover that certainly. And I'll see if I can do that in one of the next webinars. Minimum sample sizes. Minimum sample sizes, Russell. Oh, no different than anything else. All right. In general, I think if you have fewer than 8 observations, there's nothing you can do. I don't think computing a mean is worth doing with less than 8 observations. How about that? You don't know the extremes. You don't know the high values and the low values because you probably have not observed them. So with any field type data, if all you've got is 8 or fewer, about the best you can do is report the 8 numbers and say, here they are. All right, between 8 and 20. Between 8 and 20 observations, you're going to have to assume some sort of distribution because you don't have the extremes. You don't have the high values and the low values. You can't compute a 95th percentile without having at least 20 observations, I think. Something like that, 19 or 20. So you don't have something that you can credibly say is the upper end. So what do? You assume some sort of a distribution. I would use ROS to do that because you want to leave some room for the fact that because you have small amounts of data, you really don't know what distribution to fit. ROS is much less sensitive than MLE. Last question that I'm going to take today, but I will answer all of them in an Excel file and post that for you. So look for that if your question was not answered, and I apologize. There's just a limited amount of time. So last question from Ed. For a Mann-Kendall test for groundwater data, can these methods for non-detects be incorporated into the Mann-Kendall test somehow? Yes, by using a different version of that test. Actually, if there's one detection limit, the Mann-Kendall test itself would be fine. But the slope coefficient, if you want the Sen slope, still is not going to be great if there's more than 1 or 2 non-detects. So there are better methods. There are methods that were developed to modify that kind of procedure. It goes usually by the name the Akritis Thiel-Sen procedure, ATS. That's available in the NADA package. We discuss it in the course that's up on the website, and it's in the book in 2012. So it's basically a Mann-Kendall kind of procedure to do a trend test, just where you incorporate multiple detection limits. So you can take a look at that, the ATS procedure. It's very good, and it should work just as well as the Mann-Kendall test does, given that you have some values that are non-detects. You don't want to substitute in trend analysis. That's the worst case, because detection limits generally in labs go down over time. And if you substitute half, all those numbers you just stuck in there arbitrarily are going down over time, and it's a great way to see a downtrend that's not out in the field. So don't do it. Use something else. That's it for today. Thank you for attending, and I will get back with you in July.